Welcome to the presentation of my work with the title on the importance of global stability for discrete gridshells created by the Trust Network Analysis Form Finding method. My name is Sverre Haakonsen and I'm currently a PhD candidate at the Department of Structural Engineering at the Norwegian University of Science and Technology. The work I'm presenting for you today is an excerpt of my master's thesis written in collaboration with the second and third author. The latter two authors were our supervisors during the process. So let me start by giving you a brief introduction of this presentation's content. First, I will give you some brief background on the work before a hasty presentation of the Trust Network Analysis method follows. After that, we will take a look at the methodology used before I will present a case study of the work and the results that came out of it. Finally, hopefully we have time to wrap it up with a quick discussion about this presentation. The background and the motivation behind this work is the flexibility provided by the algorithm-aided design and our curiosity for grid shells and form finding in a digital environment. So, as structural engineers, we had little to no knowledge about how to approach such geometries during our studies, and a master thesis was therefore a perfect opportunity in creating and evaluating efficient structures, which is also visually appealing, and this is what drove us towards the work. And we quickly realized that although several form-finding methods are able to establish a global equilibrium situation for a given loading condition, they do not tell you anything about the stability of your design. And consequently, we looked at providing the designer with feedback on this without having to establish a complete finite element analysis. And this resulted in a plugin for the visual programming language Grasshopper. Before I present our methodology, let me quickly explain the selected form-finding procedure. So the Trust Network Analysis is a form-finding method by Philippe Bloch from 2007, initially designed to evaluate masonry structures. It works by assuming that only vertical loads are present, which allows us to project the geometry down into the two-dimensional plane, where we can solve the horizontal equilibrium by the use of connection or reciprocal diagrams and graphic statics. And it's this visual relationship between form and forces that made us choose this method. We created a Grasshopper plugin implementing the TNA to test our idea, allowing us to work with funicular grid shells in a parametric environment. And from this TNA process, we get both a global shape and the normal forces within each element. And in a stability analysis, usually undertaken with the finite element software, we solved an eigenvalue problem using the global stiffness matrix and the geometric stiffness matrix, which gave us the global buckling shapes and the corresponding buckling factors. And by establishing these matrices directly with the results from the TNA, we avoid having to establish this finite element analysis, which also enables this procedure for architects. And moreover, by using the two-dimensional horizontal projection of the geometry, we can use a 4x4 element stiffness matrix instead of a 12x12 matrix for a three-dimensional beam element, which significantly decreased the computational time. We commenced a small case study to investigate the performance of the proposed method. Several rectangular grids with different heights to length ratios were designed, each with different heights. As you can see in this image here, we used width to length ratios from 1 to 2.5. And for each of these geometries, we estimated the buckling factor using the geometries and the normal forces of the element. Then we did a finite element analysis using the Karamba 3D component for comparison. And as you can see in this figure, we have compared the results of normal stresses between the TNA procedure and the finite element analysis. And a ratio of 0.1 indicates that the normal stresses are identical. And for curvature ratios above 0.6, you see that the TNA gives almost the same stresses as the finite element analysis. For ratios below this, the discrepancy is growing, and this is caused by the bending behavior of the lower shells, for which the TNA does not account for. More interesting is the accuracy of the buckling estimations from the TNA. In this figure, you see the ratio between the buckling estimations from the TNA and the finite element analysis. And in general, there is a linear relationship between these two. Note that for curvature ratios below 0.4, the results are not valid due to the lack of bending behavior in the TNA. To summarize, the proposed method shows an accurate representation of the normal stresses in the grid shells. Moreover, there is a linear relationship between the buckling estimates from the TNA and the finite element analysis. Although for curvature ratios below 0.4, the results are not valid due to the lack of bending behavior of the TNA. So in the future, I would like to include cases with more diverse and complicated geometry to further investigate this. So thank you all for watching, and if there's any questions, I'll be happy to answer them.